Hmm. One sec.
All right, all right. Hello, everyone. Um, I don't know why my camera is so small. Yeah, all of a sudden, I don't know. Let's see. Okay. Um, welcome. We have one viewer. That's great. So, um, basically, we're back. We're back on track. It's time to continue developing our red black tree. This has been an absolute hell of a journey, and I mean that in the literal sense. Um, Coding often involves these things, so bear with me. But it is part of the essence of coding. It's maybe not the most fun part of it. So the reason why I want to finish the red black tree now, like today, I'm going to finish that today. And if I have to stay on stream for 4 more hours, I will do that. But I am going to finish the red black tree, at least the insertion. The reason for that is because the red light tree, it's like it's like not the main part of our memory allocator. The main part, well, I guess it kind of is, right? Like the memory allocator is like a fun part. It's what I display in the title. And although the red black tree is part of the memory allocator, well, we sort of, we want to move on. So that is my compromise with all of you today. If we need to have 6 hours of stream more, completely willing to do that. So, let's go. I guess. I don't know. We'll just pick up from where we left and we will continue. So, if anybody doesn't have any context to what we are doing, why has this moved from where it was? This is very strange. Um, yeah, it's still here. Then I can increase the size of this to what it was before, which is this. I think this was the size before. I have no idea. It's okay. Um, so basically, what we were doing before is we had finished coding the insertion method allegedly. The problem is that when we try and test it, so when we reset and then we try to compile and then we test it, we get a segmentation fault. You may be asking, Sharif, where is the segmentation fault? And I will tell you, I have no idea. There's a reason why this channel is called SharifSegfaults, and it's because this is a very common mistake on my part. But, as everything in programming, we will solve it. We will come out victorious. I'm honestly just trying to hype myself up for the next 4 hours of debugging that we're going to have to go through. So currently, that's the landscape. That's how things are looking right now. We have this little guy, right? Testarbitry.c++, and he's a little, it's a little test that we have created in order to measure how things are working. And right now, the test that's costing us everything is this one. Right, we are following Michael Samble's video, and I'm just using sort of his example as a way to test the code. A very simple, a very simple example. And so you can see first we insert 15, right? So then we're gonna continue, we create a new node called 15, value 15, right? And the root is no pointer, so we simply insert 15 as exactly that, right? The root. Now we continue, we assert that they're equal. They are indeed equal, these two trees. Which two trees? Well, we expect our RB tree to be a single tree of, right, a node that's colored black and has value 15. Let's continue. Now we insert 5. When we insert 5, we go through all of this, right? Then we try to find the root. That's the only thing that we have. And so we say, okay, print what the color of the current node is, current being the root. It's black, which is 1, and red is 0. And then print whether or not the color is equal to black. This was just the debugging statement that we had before because some weird things were happening. So now we return. I would simply say, we don't concern ourselves with this. There are no problems. So we continue. Return. Now we go here and then we check whether or not those trees are equal, and they are indeed are. The problem comes when we insert 1. So when we insert 1, what we should be seeing is this. Is we have, I'm going to grab a pencil for this. We have, oh, whoa, whoa. That's really thick. Okay, let's go with, yeah, perfect. We have 15, right? 15. And then we have 5 to its left. 5. And 5 is red. So I'm just gonna, color it red. 5 is red. Now, the situation at hand is that is the worst 5 I've ever seen in my life. What? Yay! Okay, perfect. So 5 is red. When we try to insert 1, we're gonna end up with a red 1 over here. And remember, the rules of red-black trees prohibit this, so then we need to fix this problem. My hypothesis is that that's where the segfault lives when we try to fix the problem, but we'll see. So the new node is now a node that has 1 as its data, so that's the new node that we're going to inject. Now we continue on. Then while true, what we're going to do is, okay, the current node that we're taking a look at should be, let me sort of shrink this down a little and expand this. Yeah. The current node should be the node 15. Yes. So we see it's smaller than that. And then we're going to go to the left, right? Then we continue. Now we're looking at node 5. And then we're going to compare them and we're going to see that 1 is smaller than 5, which means we need to insert it to the left of 5. We link the current node, which is 5, with the new node, which is 1. And after that, we should be done. Because current now has 1 as its left child, and 1 has the new node. 1 has 5 as its parent. So we should be completely okay. And then after that, right, when we try to print this, right, so we see that there's a problem now, right? We have inserted 1, but we have a problem. The problem is that now it's 2 reds living together. And welcome everyone that's joining the stream. We are developing a red and black tree because that's what we're going to use for our strategy to discover the best fit block for a memory allocator. Okay. Now, when we continue, we say, well, the current, so cur, which is our 5 in this case, is not black. That means there may be a problem. So what we're going to do, okay, fix this, yeah, okay. What we're going to do is we're going to go through this loop, fixing all the errors we find along the way. So currently, right, we continue, and then we say, okay, is the new node the root? No. So then we skip that. Is the uncle of this node red? No. So we skip that. Now we check, is this a triangle? And the answer is no. This is actually a line. So that should skip the if. Yes. And then now we check if it's a line. It is indeed a line. So we should enter that if. Great. So now we make the grandpa of my new node be red. So that's 15. Now 15 is red according to our code. Now 15 is red. Great. Now we make the new node's parent, so that's 5, change its color to black. So that's what we're going to put in here. Blah, 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 blah. Okay, 5 is now black. Great. And then what we're going to say is we're going to see whether or not this is a sort of left line or right line. If it's a left line, then we need to turn the tree in this direction, right? We need to sort of right rotate on the grandpa. So right rotate on the grandpa. Currently line dir is -1, which means that it would be smaller than 0. And so now this should enter right rotate. So we enter grandpa, yes, but then we should enter right rotate. Yes. So when we enter right rotate, we say, okay, the node, we're rotating the grandpa, so the node on the left, its parent is no longer 15. Great. Now, if my node has a parent, which in this case 15 doesn't have a parent, so we skip that, then we save the left-right grandchild, which is just null, and then we link the node to the left of 15 with 15, and we put it to its right. That doesn't sound right. Node left. Oh, yeah. We make 5 the new parent, right? And we make the current node, which is 15, the child on the right. So now, despite 15 still pointing at 5 as its child, we need to take 15 and make 15 its right child. Now, we tell it that node left is equal to no pointer, so we forget about this connection. Great. And now what we do is we say link the node, so 15, with the left sort of grandchild, which was nil. So 15 will be pointing at nothing. And there we have it, right? Now 5 is the new parent. So if we were to move things around, this guy will just be moved here, and then this guy, again, moves here. There we go. So this is what we should have by the end of it. But there is some weird sort of seg fault in the middle of everything. So when we link, everything should be fine. And in here, there may be a seg fault, since the grandchild is nil. That's what the seg fault is. Oh, let's go. Okay, we know where the seg fault is now. And it's the fact that we didn't check whether or not this thing was a null pointer. If to be child, right? If the child is actually a thing, then change its parent. Awesome. Okay, I think we can reset now. Oh, shoot. Ah! No. I don't want to execute that. I want to recompile. Reset. Up. No. Okay, reset. Then we need to go up again. Then we need to execute. All right, we need to execute this. Assertion failed. Okay, so it seems like right now we have the function worked, but it's telling us that whenever it does the comparison on the test, right, whenever it's trying to compare these two guys, it's saying that the number of nodes is different. It's saying that this tree, the tree we've been managing, has a different amount of nodes than this. And I don't know why. Um, that's a great question. Um, let's see. After that right rotate terminates, do we have anything else that happens? I think that that might be the mistake, is the fact that we enter the line thing, then we break. Well, actually, no, we break out of it, which means that we go back here and then we try and check what's going on. So I think the problem may be in the function that computes sort of the change from the street. Oh, there you go. There you go. We haven't updated the root of the tree to be that guy, right? So I think, okay, I see. Um, what can we do? So I think the more reasonable approach would be to simply include. Okay, so inside of this red black tree, rather than storing a pointer to the root itself, we could store a pointer to like the start. Right? Like I don't know if we're understanding each other on that. It's like you know, like make the root this thing, make this variable like start, not point to the root, right? Oh well, what am I saying? Yeah, not point to the root, but to a node that points to the root. So that way, whenever the root is swapped, the parent is updated, and then no, it makes sense. It makes sense. But I feel it would be a little bit cruel. I feel this would lead to a very bad design choice. We would instead want the let's think about it. We would instead want the node. So whenever we update this here, right, we're making like if so here, right? We're saying that if you don't have a parent, that is if you are the root, then we we skip this line of code, right? But what we actually want is to update the red and black tree's root pointer. The only problem with that is the fact that, that this right rotate doesn't really have any sort of idea of what's going on, right? It doesn't know that it's in the context of a red black tree. So I think the solution proposed before is the one that we're gonna have to end up using, where we simply point the root, this thing, the start, rather than the root, we make it point to a new node, right? Node T, and I mean the color of this node doesn't really matter. It's black. And then see, but there's something that sort of that feels wrong about this. We shouldn't be doing this. There should be something else going on. Like, because we use the root multiple times throughout a program, right? Actually only once. Well, no, we definitely use the root more. We use it here, here. Yeah, it seems like it would be natural for the root to point to whatever is happening. But to make things sort of easier to code, pointing stuff at the root is the best thing to do. But then how do we notify the root that that's what's happened? Um, oh wait, when we rotate, we return a pointer to a node, right? So what that means is that on right rotate and left rotate, we can simply make it equal the root? Question mark. Yeah, this is very bad. Okay. So what I'm going to do is I'm simply going to do what I just suggested. It's gonna have a start here. I need to update the constructor for node where it can accept all of the parameters. So it accepts a color, then a value, then it accepts the left and right, node star left, node star right, and then a node star to the parent. Yeah. And so now the only thing we do is, we use an initialization list, which is what I think I should have used here. I think it's better. It's a little bit more readable. Where we have data, there it's the value. Great. And then, whoa, what's going on? Oh yeah, great. And then we have color and data take values here. So here we have color, and then data gets val. I prefer to have them on the same line. And then over here, it's more of the same, right? And this needs to have a closing bracket where we have color gets the value of color, data gets the value of val, left gets the value of left, right gets the value of right, and parent gets the value of parent. Awesome. So now we have everything. And here, when we create the root, or what previously was the root, now it's start, we're going to proceed with that. The value, which I'm just going to say it's 0 to make some sort of neutral value. Then I'm going to put a null pointer in. And then for the left, for the right a null pointer, for the parent a null pointer, and yeah, I think that's all. And the only thing I'm going to do is I'm going to tell this guy that its child is the root. Yeah. Okay. So what we can do now is we can perform or like have a little attribute that is instead expressed as a function, right? So it's sort of like we compute the attribute. So a node t star called root. So when people want to access the root, they just call this, right? Root. And so I think I need to send a reference to exactly that, to that pointer so that it updates what I want. And we are going to say the following. I'm going to return starts. Let's pick one side. I'm going to say right child. So the picture looks something like this. If maybe I haven't expressed myself very well. Whenever we perform a right turn of the tree, why does it update back? Okay. If we have something like this, right? 15, then we have 5. And then we have 1. And we want to perform a right rotation, then we end up with 5, then 1 on this side, and then 15 on this side. Right? The only problem, or like the main problem, is going to be the fact that everything is great, but we need to update the sort of red black trees root pointer, right? It's originally pointing at 15, but we need to update it to point to 5. But in our code, in the rotate section, right, over here, so right rotate, we're working with nodes. So there's no way we can access the member variable root of the red-black tree, right? And that generates a problem. How do we make it so that rotations allow us to update the root? The solution I propose is very simple, but if you guys in the chat have like better ideas, then let me know. And is that we're gonna have a ghost node over here. So 15 knows 5 is its parent, 5 knows 15 is its child, 5 knows 1 is its child, and 1 knows 5 is its parent. I'm gonna have a ghost node. So root points to this ghost node. And this ghost node is going to point at 5. But 5 is not going to point back at it. Right? I think. Question mark? I think so. Right? Because, well, actually, no. For the way we have coded this up, we need 5 to know that that's its parent. And so that way, whenever we access, whenever we perform the change, say we want to left rotate now, 5 will know that it has to tell its parent that the new child is now 15. Okay? Hopefully that's clear. And the way we're going to achieve that is through the code over here. So there you go. So start right. Okay. What are we supposed to do? Start right. That's what you get back. So yeah, I mean, I guess it's fairly simple. I guess it would just be this. Whenever we update the root, yeah. No, okay. Whenever we update the root, so now we gotta look for uses of root in our program. For example, here, right? So the current would be equal to root, right? But like as a like the function. That's root. Then here, if root is equal to null pointer, then root is equal to new node, and then root's color is equal to black. And if root is equal to the new node, then that, and then that. Perfect. So we only need a minor modification, which is whenever the root is first created, we need to point its right child, or like, well, I guess it already makes the new node. Yes. And then, uh, well, I guess the better way to do this is to link the start with the new node and link it on the right. So that way, the start now points to the new node points to the start as its parent, and we put it on the right, and then root's caller can still be changed. Sounds great. So I need to find, yeah, this print statement we don't want, and this thing we need to change back to color of current. Awesome. All right. So, okay, I think this solves the problem. I do have a question. Properties. Well, functions as properties in C++. So there's something I don't know about the language, and it's that Python usually, yeah. Okay, language support for properties. I see. Um. Okay, no, that's fine. I thought because Python has like the little syntactic sugar where you insert like at and then property, and then that makes sort of the function behave like a property. That is, you can just instantiate it. You don't need the brackets around it, these guys around it, or any stuff like that. We could overload this to have all these operators, but that is just completely nonsensical and would make the code impossible to read. I think the reason why, so it is very important to sort of note what this is. This dot needs a clarifying note that says ghost node that points to the root of the tree. We need this here so that when rotations are performed at the root, we can still, from the RB tree, tell who the new root is. Perfect. So, and now, whenever we perform this insertion and over here we link this, we're just going to say, look at comment about start. And now people will know why we're linking this to some random guy. Great. So if the tree is empty, go down the tree until you find the insertion spot. Every time we solve an error, make the current node post as the newly inserted node and make a parent be the current node. We rerun this until we reach the root. And this is a problem. If the root is equal to the new node, oh, that's actually not a problem. That's great. All right. Let's try that one more time. Oh, shoot. What's going on? Test RB369. Okay, yeah. We updated the thing. We cannot access the root anymore, so this guy will have to call root instead. And that's it. I suppose? Question mark. Why are you not? Okay, yeah. That is great. So now we compile this, and we're gonna run this again. Test RB3. Success! Success! We did it! Yo! Awesome. Awesome. Damn. Well, that's that. I guess. Whew. Okay, so at least we passed this very simple example. Um, we are just going to make this a little bit more involved. And we're gonna differ a little from Michael's video and simply have this guy be on the side. So I'm just going to erase most of the stuff we've written down. We already know about this, but I'm gonna leave it there. So let's now draw the example we want. So first we're going to insert 15. Why is this so thick? Okay, first we're going to insert 15. 15. Then we insert 5. Then, and 5 is sort of red, right? So 5 is now red. Then we insert 1, which is also red. After this, we need to enter problem resolution, in which case the new tree now looks like this, where we rotate to the right. So 15 is black. And once we rotate to the right, we see that the root has a problem. Well, actually, when it's a line, we need to recolor also. So then I'm just gonna make 15 be red now. So we have this, and then we have 15 over here. Awesome, 15. And 5 gets converted to black. So now we say 5 is black. Great. Now, what happens if we insert, say, I don't know, 12, right? I'm going to insert 12. So 12 would go here to the left of 15. And this is a problem. We have a triangle where this guy I don't know how to call it. Let me actually go to, okay, where is the insertions video? It's here. Okay, I'm trying to see if the stream is working well. Yes, it is. Okay. Perfect.
Today we're going to learn
So
about...
I remember we have a little summary of what the strategies are. There you go. So it's a triangle. It's a triangle. Well, your uncle is red, so we just simply recolor. And by recoloring, we make this black and this guy red. 1, 5, 15. So, oh, shoot. 1, 5, and then 15. Oh, but 15. Whoa. This one is 15. 5 is the one above. And then to respect the invariant that the root has to be black, then we need to make 5 black. Good. Okay, so now what we can do is say we insert 13, right? To make this a little bit of a difficult tree. So 13. So first, I'm going to draw these, and as we draw them, we're going to know what the correct position is and what the correct everything is. So if we insert 12, 120, no, 12, we expect, so we're going to assert, we expect this red-black tree to be equal to RB tree. right? To be equal to something that has, well, a black root, which would be 5, a black left child, which would be 1, um, then a black right child, which would be 15, yeah, and then a red child, which would be 12. Great. Then we finish this here. Arbitrary type name is not allowed. What? Oh, hello. It just works okay. Hi. It just works okay. Yes. So these are red black trees. The reason why we're currently working on this is I'm writing a memory allocator from scratch, as the title of the stream says. And we have decided that the best or like the allocation policy that we want to follow is best fit. That is, whenever somebody requests a block of a given length, say 12 bytes, um, we are just going to look for the block of best fit. And in this case, we were determining how to do that. The final decision was, okay, we should use some sort of data structure to search for the best fit in the most efficient way possible. And of course, binary search trees are the first thing that comes to mind. To improve the efficiency of binary search trees, you have two alternatives, AVL trees or red and black trees. And the thing is that between those two, red and black trees have less memory consumption. And since we're writing a memory allocator, we want our memory allocator to be fast, but to use the least amount of memory, right? And compared to AVL trees, the red-black tree uses the AVL tree uses like 20% more memory compared to a red-black tree approach. So we sort of went with the red-black trees because of that, although they are, in my opinion, a little bit harder. Like they have sort of more cases to follow. And we have like a sec fault and all of that. There's a reason why this channel is called SharifSegfaults, because it is the most common mistake I make. But now it seems like the code for the insertion in the red black tree is working, and now I'm just testing it. Right now, now I'm just like drawing little trees to see what it should be and asserting that the tree looks like that, right? Assert that the red black tree looks like this, and then you just list the pre-order sort of listing of the tree, and that way we check it. So yeah, that's what we're doing right now. Thank you for hanging out in the stream, for being here. And yeah, if you're asking why are we writing a memory allocator from scratch, the reason is there's not much of a reason. This is just for the sake of learning. I am a college student, right? And I really like low-level programming, systems programming, and C++. So this is just the way I like to learn. And so we're just writing a memory allocator. like, but yeah, that's all. So here I was just creating like little trees to try and to battle test it. So right now I'm inserting 13 into the tree. And as you can see, we have a violation here, and this would be a triangle. And remember that the nils are implicitly there, and they're always black children, which means that we need to now rotate the new node's parent, as we already saw. So that's gonna mean we rotate in the opposite direction of the child. So now we need to rotate the parent right. Huh? No, we rotate. we rotated left, right? Because if it's the right child, then I need to rotate it left. Yeah. Okay. So now we rotated left, which means that this will now be 13. This guy will be 13. Oh, shoot. Oh, no. There you go. This guy will be 13. And then this guy will be 12. Great. Once this happens, we have another problem. But now instead of a triangle, it's a line. It is a line, so now we need to rotate the grandparent in the opposite, like in the opposite direction to us. And wait, sorry. Oh, new message. Also, no worries. I'll be lurking a bit. Even I got things to do. Yeah, yeah. Of course, of course. Like, you don't have to hang out for the entirety of the stream at all. People come and go, and this is just people want to hang out, contribute ideas, and also to hold myself accountable to not procrastinate and to have at least a motivation to code. Be like, nah, gotta stream today. This is my second day on Twitch, so don't have much of experience. And yeah, you can hang out around and leave the stream whenever you want. Yeah, no problem. So okay, right now, let's see. We have this violation. This is a line, right? So now we need to rotate the grandparent and recolor. So that means that when we rotate the grandparent to the right, 13 is the new sort of root. So it's going to be 12, 13, 15, but with 13 at the top. So 13, 12, and then 15, but 15 was black. And 15. And then we recolor. So once we recolor, that should be what? That should be this guy red, and then the other two black. Let me see what we wrote in the code. When we recolor, we make the grandparent's new color be red and the parent color be black. Okay, perfect. So now we recolor you to be black, and you to be red. Oh. Awesome. All right. So at this point in time, I don't think we have any violations. I think this is a valid red black tree. So this is the final state. Okay, so it should look something like this. So RB tree and then equals vector and then RB tree. And then we put this over here. And we say, well, we have a root, a black root, value 5. Now we have a left child that's black, and its value is 1. Then we have a black right child, which is 13. Then we have a red child, should be 12. Okay, 12. And then we have a red child, which is 15. This would be in the pre-order layout of things. I think this is what we expect on the tree. We need a semicolon here. Welcome all the people that are joining the stream. Whoa. Yeah, the stream. We are writing the memory allocator from scratch, but we are currently working on random black trees because that's the data structure we're going to use to find the best fit for the blocks of memory that we're going to have. And I got introduced to red black trees yesterday because the only thing I had been using so far was AVL trees. So here we are going through red and black tree hell. I feel this is... So we have exercised, I think, every single case. I think. Right? Let's try one more. One more. Only one more. I promise. Okay, 17. Let's put 17 in. When 17 is inserted, so we'll go to next, be inserting 17. 17. When 17 is inserted, we are going to find that this is a line. For our line, we rotate the grandparent and recolor. So we rotate the grandparent. Ooh, this rotation looks weird. So, well, not really that weird, right? It's just 13 and 12. Oh, sorry, actually, I can just transfer them. 13 and 12 simply get like transferred down here. And now 15 is the new root. And then this guy connects to here. Oh, shoot. No, no, no. We need, no. We need this guy yeah, to be there. And then, there you go. Okay, 15 is the new guy. So once we rotate, yes, the grandparent. And then after that, we need to recolor, right? So as we recolor, we need to... Ooh, this is really bad. This is really bad because we just discovered a problem. Previously, we were assuming that errors propagate upwards, and it just so happens that that's not the case. We assumed wrong this whole time. Okay, this is serious. Wait, no, what am I talking about? No. What was I doing? Wait, what am I doing? Whoa. Okay. Whoa. Okay. We have 17, and its uncle is red. So we don't enter the case of a line, we enter the red case, in which this just changes color to red. Ooh, okay, we got saved by the bell. What? I was so scared. Okay. Now this thing becomes black. 12 and then 15. And it seems like this is the final state of the tree. There are no other violations every... Yeah, okay. So we basically have the exact same tree, except that the colors now change. This should be red, 12 should be black, 15 should be black, and 17 should be red. Great. Okay, I think that's all. Right? I think that's all we need. If anybody opposes to the current state of things, you better speak now, because I think we are done with this little test and kind of scared to run it, but let's go. All right, let's compile this. Compiled, reset, and now we are going to execute. Shoot, no! 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 Okay, this is good in the sense that we didn't get a segmentation fault, but what this is currently saying is that our tree is failing on the comparison. Let me see. 5, 1, 13, 12, 15, 17. Yeah. No, this should be the right thing. Okay. I didn't want to do this, but guys, this is once again the boring part of the stream. We need to debug. Ladies and gentlemen. That's unfortunate, but bear with me. Um, yeah, guys, I'm sorry. I'm sorry. I'm sorry. I'm sorry, guys. Okay. Oh, wait. Yeah. So here we have this. I need to eliminate all these previous breakpoints that I had introduced for the debugging we did with let's see, arbitrary start points at it's right the black thing and it's 5. So that's 1. And then I need to stop right here. Oh, what? Whoa. Whoa, what was that error? I'm going to stop here on the insert and then we run it again. Oh, the assert happens before 17. Oh yeah, because we added a bunch of stuff before. Never mind. Okay, so we know it works up until this point, and then after 12, it's just like, run for your life. So let's see. We reach 12, and everything has been sunshine and rainbows up until this point. Now, when we add 12, ooh, we enter a problem. Okay, so the problem is at 12. Let's see what happens at 12. So we have 12, and then we go to the next line, and now the tree is there. So apparently, I'm going to draw the state of the tree according to the program. So we have the start, right, which is pointing to... What? Why is 1 the root? The root should be... Okay, well, yeah, we're not in the greatest of times. That was very odd. So I think we're gonna have to enter to the insert. Okay, so the value is 12. Remember that. The current one, it's the root of the tree. Because remember that the tree looks like this at this point in time. 5, 1, 15. 5 being black and these other two being red. So 1 and then 15. Perfect. All right. And so we continue. The tree is empty. So the tree is not empty. So we skip this. Now we go into the while true. And we say, okay, is this smaller than the root? No. So we go to the else. And we know that the root has a right, so no. And then we go to the right. So now we should be at 15. Yes. Now we compare them both. It's smaller. So then we enter this. And 15 doesn't have a left. So then we just put it on its left. We link it to 15. And after this line, the left of 15 should be 12. 12. And the parent of 12, which is a new node, 12, should be 15. Yes. Awesome. So now, when we continue, right, the current node, which is 15, so right now what it has done is this, 12. So the current node, which is 15, like the parent is not black, which means that we may have introduced a problem. We continue here, and we say, okay, while true, if the root is equal to the new node, which is not true, so then we skip this. Then we ask, is the new node's uncle red? And the answer is yes, it is red. Yes, okay, perfect. So now we grab the grandpa, which is 5, and we change its color to red. So we change 5 to red. 5 is now red. Great. Now we go to the uncle of the new node and change its color to black. So the uncle, which is 1, we change its color to black. And after that, we go to the node's parent, and its color, we make it black. Great. And then we move up the tree. The new node is now 15, and the current node is the parent, right? Current equals current parent. Great. So now we continue. We go back. We say, okay, is the root equal to the new node? No. Ooh, I see. Very interesting. Because now we try to say, okay, is the new node, which is now being, like 15 is now posting as the new node, is its uncle red? And then the answer to that should be a seg fault. So now I'm worried, why are we not getting a seg fault? Like, what? Here, we should get a seg fault. Because the new node is now 15, right? So when we try to get the uncle, we travel to the grandfather, which would be 1, and then 2, right? Oh, I see, but this guy has to start pointing at it. So when 15 tries to visit the grandpa, it goes here and then it goes here. So there's no seg fault. I see. Um, Okay, this start is generating a lot of problems. But it is needed for the sake of rotations. So I don't know what to say. Hmm. Well, how can we tell? Right, because then after that happens, well, we would have gotten a seg fault in this case. So, like, let's assume we got a seg fault. How would we have solved the problem? And the answer to that is here. We would have said, well, rather than checking whether or not the root is now the new node, we want to see if there is some sort of problem that we need to check or something like that. So let's think about this. This is very difficult. What we can do is unconditionally always color the root black. Like after every iteration, just color the root black. And like make sure that keeps happening and so on. Right, where we're setting it to a value that it already has. But I feel that's not a good design. I feel like we should proceed differently. We say k0 equals new node is the root, make it black. If the root is equal to the new node, then the new node color equals color black. Then we break. What are you watching? Hmm? All right. No. Let's think about it. If the brood is equal to the new node. Okay. So we could sort of isolate this case and say, like, if the child is black and the root is red, then just color the root, because we know that a black child won't be any problems. And so we have that kind of situation. Or the root is equal to. I don't like this. I don't like this. I'm thinking of situations where. So we know that we cannot have any problems with a black, like, child, right? Question mark. So that means we could introduce a little case here that says, well, if, let's see, we will never have problems with a black child. Great. And so what we're going to say is, well, if the color of a new node is equal to black, then we're going to move up the tree, right? The new node is going to be equal to the current node, and then the current node is going to be equal to its parent. And then we continue, and then after that, in the next case, the color of the new node is black, and then we while let's see, while new node is different from whatever start is pointed out. Yeah, and I think this fixes the VS that we were looking at before. So I think this is a better solution, right? Because we would never have problems with a black child. And if so, we just go up the tree. If the root happens to be the new node, then we're going to say, okay, now the new node is going to be, no, this is perfect. Awesome. This is wonderful. I think this solves it. I think we now need to recompile, we reset, and we're gonna have test arbitrary. Well, it was a pleasure to meet all of you. Dude, no way. Ah. Okay, it's interesting. Like, what do we do? What do we do? One viewer. Because currently, I think we can just Okay, let's compile this and debug it and see what's going on. We cannot give up. We cannot give up. We must continue. We cannot give up with the red-black trees. Never. Okay, so we go to insert 12, and let's see what happens. The root. Again. The root is. Yeah, the current one is 5, so we're supposed to start at 5. Then we detect that 12 is greater than 5, so then we go here, and then we continue our path. And then we see that it's smaller than 15, so then we link it to 15, and then we get out. Now we try and solve the problems that we may have generated along the way. We know that this is not a black node. Now, while the new node is different from start, which is evidently true, we're going to say, well, is the color of the new node black? No, the new node is 12, so no. K0, the new node is the root. That's not true. Case 1, the uncle is red. Yes. Like, if we were to imagine this tree before we even processed it, yes, the uncle would be red. So we would have the grandpa, right, be the grandpa of the new node. We change its color to red. So that's the 5, change it to red. Then we change its uncle color to black. And then we change the parent color to black. And then we move up the tree. So far, so good. But things are going to get really, really, really bad in a few seconds for a reason I don't understand. Like, we are failing an assertion somehow. So we have the new node now. Yeah, this is different from the start because the new node is now 15. And then we say, okay, is the color of the new node black? Yes. Yes. So then we should skip that node because we're never going to have problems with a black child. So the new node is equal to the current node. So that's going to be 5. Right? 5 is the current node. And the current node is going to be the start node, which should be just a bogus value. The new node is still not the same as start. And then we say, okay, is the color of the new node black? No. Is the new node the root? Yes. The new node now changes its color to black. And we break. This sounds awesome. Like, what are we talking about? Right? 5 is supposed to be black because of the red-black tree property. So now we change 5 to this. And then, oh, we have another view here. Hello, viewer. Currently, we are writing a memory allocated from scratch, but we have decided to use red and black trees as the data structure to store the free blocks. The problem is I didn't know what a red-black tree was before starting this sort of challenge. So yeah. Oh wait, it's just it's the same viewer. It just works. Okay, it's you again. Okay, I thought it was a completely new viewer. But yeah, so now we have this color, and then we break. So everything is wonderful now because the current node is the start node, which is like this ghost node that it's going to tell us where the root is. So its right pointer should be the root, which is 5, and it's black. And then 5's left child should be black and 1. Yes. And 5's right child should be black and 15. Yes. And then for 15, it should have a left child, which is red and 12. Okay, this tree is completely valid and it is what it's supposed to be. Where does it get messed up? So we continue. Oh, great. Turns out the 12 case was not the one failing. Apparently it's the 13. Like, well, apparently there's an error with 13. Let me just check that indeed 13 is the error. Let me just insert him. Oh, 13 is not the error. The problem is the 17. Okay. Let me just check that 17 is indeed an error before I start debugging something that is not supposed to be debugged. Yes, okay. So we have the problem with the assertion at 17. And it's gonna be a little bit bad because, okay, so when we insert 13, we have this, right? 13. And then once we insert it, well, we have a triangle. Our uncle is black, so we rotate. And then it should be 13 and then 12. Great. So now we have this other problem, but this is now the case of a line where we simply rotate the grandparent. And then, so now it would be 12, 13, 15, the same, just like rotate it. So 12, 13, and then 15 black, 15. Good. And then we also need to recolor. And we recolor, I think it's, yeah, we make this one red and the other one we make it black. So this 15 becomes red and the 13 becomes black. Great. The 13. Oh wait, new message in chat. Yeah, red black tree logics always have confused me. Yeah. No, for sure. It's like it is such a simple concept to look at in your head, but like when you try to translate it into code, it's just the most hellish nightmare you've ever seen. But yeah, I mean, this is the tree we end up with after we insert the 13. With that context in mind, we must proceed to see why 17 woke up with the wrong foot today, and it's making our life impossible. F5. Okay. We insert Mr. 17, and let's see what happens to him. So we say that the current node, it's gonna be 5, the root, yes. Then we go down and we say, okay, 17 is greater than 5, so we go here, and then we say, well, go to the right. So now it should be 13, yeah. 17 is greater than 13, so then we should go to the right of 13, go to the right, and it should be 15 now. 17 is greater than 15, so we should go to the right of 15, but 15 has no right child, so now we make 17 be 15's new right child. We link them together. So 15's right child should be 17, and 17, which is the new node, should have 15 as its parent. 15, and it's red. Yes, everything's working as usual. Now we break out of here, and we see if we got any problems. So what we have is 15, and then here's 17. And we check for problems. We do have a problem, right? We have red and red together. That's a no-no. So the new node is not the start. That's true. This is not a black child. This is not the root. But my uncle is indeed red. So we enter this case. Whoa, it's working as expected. What the hell? And we make the grandpa be colored red. So you change your color to red, 13. And then we change the uncle to be black. So now the uncle, which is 12, is black. And then the parent of our node, which is 15, changes its color to black. So now 15 is black. Good, right? Yeah. Are there any more problems? Well, I don't see any, right? The number of blacks to any child is still the same. The number of blacks, there are no reds together. The root is indeed black. Okay, yes, this is a valid tree already. So now we make the new node. So the new node was 17, but we don't know if there are any problems. Like right now with our vision, we can see that, but the program doesn't know that yet. So what it's gonna do is it's gonna pose the parent as the new node, as if we had just inserted the parent. And it's going to check for errors, right? It's going to make 13 believe that 15 was just inserted so that he has to check for errors and say, like, were any of the transformations that we just performed, like, did they generate any sort of mistake that violates the rules of a red back tree? So we continue. And the new node now points at 15. The current node points at 13. The color of the new node is black, which means we cannot have any problems with a black child. So we simply go up the tree. The new node now points at 13, and the current node now points at 5. So we're looking at these two. We're telling 5, like, 5, check if there are any problems with your child. And then we continue. So now we're going to say, is the color of the new node black? That's 13. No. So we skip that. Now we say, well, is the new node, right? Here's your new node, is the root. So this doesn't apply to us, right? The new node is not the root. The new node is 13. The uncle is, okay. I'm starting to see the problem here. We have reached a moment in time where 13, right, we're like, there is no problem, yet we go through the cases as if there was one. So whenever it checks, like, take a look at this, right? Uncle, right? So what it does, 13, is it moves up and then up again to find the grandfather, and then finds the uncle, which is a nil over here. And it's black, which is fine. It's not going to enter here. The problem I have with that is that this start should be a ghost. So had this start not been there, we would have incurred in a seg fault. So there's something wrong with a lot. Like, we cannot have it check at this point in time. Right? And this sort of faces again the problem that we had before. It's just that now the right child of the root is red instead of black. So we simply need to stop it whenever we know that we have reached the root and there's sort of nothing bad happening. So yeah, well, I guess that instead of skipping the, like, I guess this is a valid metric, but we would also need to account for the fact that, well, if, right, the root is our current node, sort of very similar to this, to this case over here, then we simply say our quest has ended. There's nothing else we need to do. We just want to make sure that the root's color is black. I think this could just fix all of our problems, right? Because, yeah, and then we can erase this line. And then it's going to be way more concise. Avoid visiting start if it is avoid visiting start, right? So I think this should account for it. Question mark. Error while processing. What? Expression is not assignable. Oh yeah, color is supposed to be just very, yeah. So we just set its color to this. Yeah. Great. We insert. The C++ extension Visual Studio Code is really slow. Like, somebody has to work on this at Microsoft. Reset. Okay. And then let's run it. Please work. Okay, we have another problem. This is not great. Dude, Sharif slow descent into insanity? Bro, real? Yeah. Like, absolutely insane. Um, but I believe we like we will succeed. I think we're very close because we are creating the tree in the right way. Like the tree we have is at the end this. Is just that we're failing to stop at the right moment. So that gives me like a lot of hope. Um, let's see. We continue. Okay. We are currently looking at the new node in the current 15. Yeah. So we just recolor this. Now we should be looking at 13 as the current one, and then 15. Okay, new node points at 15. Um, the current one is not the root. Then there's really no problem with 15, but we're just gonna go through these cases. This is not a triangle. This is not a line. Oh, what? Oh, yeah. Okay. So, that previous line that we had, that black children never generate a problem, was actually a fundamental piece of our code, and I deleted it. Black black children will never be a problem. Um, Let me think about this because I think we had such a beautiful design where it was like case 0, case 1, case 2, case 3, and we are like it was sunshine and rainbows, and now I'm just patching the solution. Now I'm just saying like, all right, if the current one is the root, then stop. And also if you see a black child, then that's fine. You can just continue. But what happens if we have something like, if we had eventually a tree becomes like big and then it's like something like this, right? 18 and then sort of 19. Right now, as the tree is structured, this would be impossible for a red black tree. But just like bear with me, right? Like imagine this had more stuff in here and etc. We would be like, okay, 19, la 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 la. There's no problem here, right? 18, there's no problem here. 17, there's not a problem with 17. But 17 is not the root. Or like, yeah. Like the current one, which is 15, is not the root, so we skip that. 17 is not a black child, so we skip that. And then we go back into the cases as if 17 was a mischievous guy. There has to be a way in which we we can like in which we can like check whether we're doing something wrong or not. Um there has to be a way. Let's see. Oh, I need to check. Best promotion. All right, buddy. You're getting banned, buddy. Like what? Okay. I'm slowly descending into insanity. It's 10 p.m. where I'm at right now. I'm on PST time. I go to bed at 10 p.m., but I made it a goal of today. We're going to finish the insertion for the red black tree, no matter what happens. If I have to stream for 6 hours, in fact, I mean, I started the stream at 2 p.m. Like, I've been 8 hours here. Well, 6 hours and then took a break, and then we've been here an hour and a half. So, like, I'm going to stay here. If I need to stream for 6 more hours, I will do it. But we're finishing Red Black Trees today. So like the main question or the main thing that I just mentioned was, could there be a way in which we could simply just have detect whether or not we have a problem? And I guess that's fairly simple. I don't know why I've been complicating myself with this. Wait, new message in chat. Yeah, it's pretty late, isn't it for you? Yep, it is 10 p.m. It's about 10 p.m. for me, but that is completely fine. I mean, programming it. I mean, also 2 p.m. Geez, yeah, we like yeah. It is kind of crazy. Programming is kind of addictive though. And the reason why I started the streams is, as I mentioned, to hold myself accountable and really finish stuff. So that's exactly what I'm doing in between seg faults, in between learning all of this, because we were also planning the memory allocator. That was yesterday, and so now we're like in the nitty gritty of the implementation. So I've been in here since like 2 p.m. Um, so it's a bit of a, you know, it is the life of it is the life of the programmer, I guess. I don't know. But I feel like a way in which we could solve this is, I mean, I guess the question is stupid, right? How do we know if there's a problem? Well, we simply check whether or not the new node and the current node are both red. If they're both red, there's a problem. And if they're not, then we're fine, right? Am I inventing like a, is that just, I think that's just it, right? Like, if there's no problem, we just continue. Happy face. So, if we have a, let's see, if the color of our new node is sort of different from red, and the color of the current node is different from red, sorry, or the color of the new node or the other node is different from red, then we can skip this. We say the new node is just equal to the current, and just go up the tree, right? And then make the current be equal to its parent. Okay, wait. I just saw a message in chat. Oh, you're in summer school? But also, yes, I see you. I'm interested in that since I love things like this. Dude, awesome. That's incredible. I am not in summer school right now. This is just like a self taught, I just woke up and I said, let's write a memory allocator from scratch because I want to know how malloc works. and then we started our descent into this hellish spiral that has only started because, like, this is a red black tree, right? Like, we haven't touched the memory allocation aspect of things at all. We're just coding the red black tree, which is kind of interesting. And yeah, you're interested in this since you love things like this. That's awesome. I mean, low level programming and, like, there's a beauty to it in the sense that it's looking at these things that everybody takes for granted. No, it's like memory allocation. Like, oh no, I just call malloc or I just call new, and then it just magically happens. But then being behind the scenes and really taking a look at how everything works is a very magical feeling. But it also leads to sessions like these. I guess this is the sacrifice we have to make. But yeah, I don't know. Are you also in some sort of school? Do you work? Because currently I said I'm not in summer school, but I'm like in an internship, so I still have to obey, like a schedule and stuff like that. But this is worth the sacrifice. Oh, thank you for the follow. Yay. We have 5 followers now. That's great. But yeah, that's all. So we will see if it works. And yeah, I'm glad you're hanging around. Let's see. There's no problem. We just continue. Will that mess up our situation here? I don't think so. Okay. Let's kill this. Then let's reset. And then let's compile this again. Reset again. And let's. Okay. Well, this is the usual life we have to follow. So let's see. We step into this. We continue. We say, okay, blah, 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 blah. I just want to go to the part where we start solving the problems. Okay, here. We recolor. That's fine. and then we move up the tree. So now the new one, I'm gonna erase these things because they're gonna confuse me later. Perfect. So now we're at 15 is the new node, 13 is the current node. Yeah. And in that case, they are different color, which means that there's no problem. Yes, exactly. So we move up. And now, what? Oh, we didn't put in continue. We didn't put in continue. So we're still evaluating the cases. Continue. Okay, reset. And then we compile again. Oh, sorry. Let's compile again. Then we reset. And then we run it. Oh, we are now failing at a previous test. Ah, how could that change things? Oh, I think I know how. It's because if we apply that logic, so like imagine that the root was instead of like this 13 was black for some reason, and this 5 was red. Then we look at it and we say, oh, they're different colors. Oh, that's fine. And then we just continue, and then we never change the color of the root. And then the start, I have it displayed. I have it have color black. So now it checks these two and says like, oh, they're different. So there's no problem. And then it continues. Yeah. So I think the thing we just need to do is this. Like, if the new node is the root, then make it black. Otherwise, we just continue. Okay, I need to make this code more beautiful because absolutely insane the way it looks like right now. Okay. Bring in the drums. Bring in the drums. Let's see. Da 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 da. Oh my god! It worked! Let's go! Let's go! The example worked. Yeah. Wee. All right. Oh my god. This is so. It worked. Let's go. It's a success with the little glasses over there. So it means we have a decent insertion. I want to try one last case, which is when this right side overflows. Because if it overflows, then it's gonna trigger like a chain reaction because it's gonna flip this tree, and now this is gonna be red, but this guy is not gonna be black. Like let's just try one last time. Arbitrary.insert, and I want to insert 19. And then what should the state of the tree be after inserting 19? I for some reason I just want to make sure that our insertion is coded correctly, because if it isn't, we're going to go through the worst of times in the future, because we're going to be looking at trying to find bugs, and we're going to say like, oh no, our insertion was coded correctly. No, right? So that'll be a problem. And this 13 was red. Yeah, okay, I'm not hallucinating. Yeah. Okay, this 13 is red. This 13 was red. Now we have that. So 17. Okay, perfect. What do we do now? we go and say this. So my grandpa, right? And yeah, we have Michael's video here. Yeah. So our uncle, which should be this guy over here, is a nil, so it's black. So it's a black line. We need to rotate the grandparent and recolor. So 17, okay, it seems rather simple though. 17 is the new parent, and then 15 is the subordinate. And now we recolor. And by recolor, it says change the old guy to red, and then change the new one to black. Right? I think that's the thing. And yeah, it preserves the tree wonderfully. Okay, so there shouldn't be a problem with that. You simply copy this, copy that. So it should be 5, 5, 1, 13, 12. We're just doing the pre-order traversal of the tree to represent it. 17, then 15, then we're doing color. Oh wait, these things change color. Red, then black 12, black 17, red 15, yeah, and then red 19. Good, that should pass, no problem. And then arbitrary.insert. Last thing, I promise, insert 21. And that's the way we can tell whether or not we've done a good job. Although I'm pretty confident now that we indeed have a correct insertion method. So I don't know what to expect from that. Because when we insert 21, I hope this is the one that triggers the chain reaction. Because 21 gets inserted here, right? And then we say, okay, our uncle is red, so then we recolor. And by that, it means sort of we propagate the darkness of 17 down the tree. So 17 now becomes red. And then this guy becomes, these two guys become black. So 15 and then 19, right? And what? Oh, yeah. Okay, great. We have two reds over here. Yeah, I was just like, it's impossible we don't have a conflict up until this point. So we go up. There's no conflict here. And then we need to change this here. There's two reds colliding, which means that now we have to fix this. How will we fix this, Sharif, you ask? That is a great and wonderful question. We see that our uncle is black, and this is a line. And if it is a line, we need to rotate the grandparent, which should be 5. I'm telling you, this, like, once we overflow, this whole set of rotations is going to change the tree so much that it's going to be kind of painful. So we rotate the grandparent in the opposite direction. So 5 changes to the left. So I guess we do... I don't want to lose the current progress of the tree in case I mess it up. So let's just do it like by hand. Yeah. So it would be 1, then 5 would be its parent. 5. And after the rotation, 12 would be 5's child. 13 would be the parent of 5. We're sort of rotating it to the left, right? And then 17 and 15, which is black, and 19, and then 21. And then we need to recolor. So when it says recolor, I don't remember what the recoloring part of it is. I think we wrote it down in the code, so hopefully we can recover it. Case 3, recolor. It's the old grandpa is red and the parent is now black. So my old grandpa was 5. Yeah, 5 was black before. I don't know why I had it red. 5 was black. 5 is black. Now it's red, and then the old parent, which is still the parent, is black. And it seems like we end up with a valid red black tree. Okay, that's perfect. This is the last ultimate test. I promise people. I know I've been really annoying adding more and more test cases. I'm just paranoid. I'm just a little bit paranoid, so better sure than not sure. I don't know. Like, I don't know if there's a saying for that, but like, better sure than not sure. Red in 5. And then we're going to do color. I'm going to go for black 1. And then we say black 12. And then we say color the black is 12, and then 17 is red. Once again, this is the pre-order traversal of the tree. Color black. It's gonna be 15. And hello to the new viewers. There's 3 viewers right now, which is great. We are currently coding a memory allocator, but you may be saying, I'm sure I don't see that's a memory allocator. You'd be completely right, and the reason is that we are coding a red-black tree. Why, you may ask? Well, because it's the data structure that we have decided we will use in our memory allocator to store the free blocks. The thing is, I have no experience with red-black trees, and so we're coding one from scratch so that we can use it in our allocator. There are thousands of red-black trees on the internet, but when I say coding a memory allocator from scratch, I really mean coding a memory allocator from scratch. So that's what we're doing. 13, 5, 1, 12, 17, 15, 19, 21. Yes. All right. Once again, bring out the drums. We are going to see if this works. Perfect. Okay, we can now be a little bit more certain that our algorithm indeed works. Awesome. I mean, I have just tested the right side. Like, I've been just inserting a bunch of stuff on the right side. We will need to test the left side, but testing is really boring. Like, I'm just going to assume that it's correct. Like, at this point, like, I'm just going to assume it's correct because we have done enough testing to the point that, like, we can feel fairly confident. Fairly. Emphasis on the fairly. So, great. Dude, we achieved it. We have an insertion. We are fairly confident it's correct. And there you go. Wow. We will have to make this code a little bit prettier, in my opinion, because it's like, it looks pretty right now. Like, I feel like the design decisions we've made so far are really good, right? Like, the code is very readable, right? If the color of uncle is red, then may grandpa's color be red, uncle's color be black, my parents' color be black, and move up the tree. So I'm very happy about the decisions we've made so far. And I feel like a good reflection of good decisions comes in the form of sort of how easy it is to read the code. Unfortunately, I feel this is a very easy to read code, right? If this is a triangle, right? If this is a triangle and it's a left triangle, then we rotate to the left. Otherwise, we rotate to the right. Then we move up the tree. So, yay. Okay. Oof, we have finished insert, and as a reward, we get to write the doxygen for insert. Um, and the only thing I'm just gonna put here is just a little brief. Inserts a new element into the the RB tree. Great. All right, insertion is there. We have it. I think we can. I said that today we would at least finish the insertion, but screw that. I'm continuing. I'm continuing, and I hope to finish the entire red black tree class today. Remove. When I take a look at remove, it gives me the chills. Remove is like a scary guy. If we dealt with insertion and it was so long, like the coding process and the amount of bugs we had, removal is going to be absolute hell for us. But that's okay. But yeah, I don't know. For find, I think it's gonna be relatively simple. Question mark? I think so. Well, whenever we need to find, so there's something that we need to keep in mind. For find, we want to end up with the sort of last fit, or like the biggest fit. Although, actually, never mind. Never mind. I don't know what I'm saying. Like, in the context of our memory allocator, we don't want to find the specific value, right? If the specific value is there, that's great, right? That's awesome and incredible. But if it's not, then we need it to return the one that's greater or equal to it. There may be a value that's smaller than it, but really close, but that's useless to us. We need find to return the one that's sort of greater or equal. I think we're going to code find in that way. Maybe question mark, I don't know. So let's actually write the doxygen comment brief. Returns the key is the element whose key is a lower bound to the task key. Right? So we should account for a lower bound. And in order to do that, well, we simply need to store a variable of which is the most lower bound of them all that we've seen so far. And I think that during insertion, we already had to look for this to navigate down the tree. And I genuinely think we can just reuse this piece of code that we wrote before. I'm just going to have it here on the side and write it down again just to see if there are any logic errors. I don't think so because we already sort of tested it, but it's okay. I mean, while true, right? If the current value you're presenting me with is smaller than me, or like if I am smaller than the current node, then we need to go to the left. To the left. Otherwise, we need to go to the right. It's really simple. And then once we're done, we just return whatever the current value is. Right? So the question is, does this code, as it's written, provide us with the lower bound? So let's see. We only go to the left when we are strictly smaller than the current node. If we are greater than the current node, okay. Yeah, so it is possible that we end up with a situation like this, right? Where say the value is, I don't know, we're going to say 12, right? Oh, well, no, not 12. imagine that instead of 12, this was like 11. So then if I ask for 12 bytes, then what's going to happen is we're going to go here, then we go here, and then we go here. But 11 is not enough to suffice our request. So as we go down the tree, we need to keep track of the lower bound. So we still need to do that. So never mind, lower bound. And then what we're going to do is we need to also keep track of the current node. So current node and lower bound. And then if I am strictly smaller than whatever we had, then that is a candidate for the lower bound. Lower bound is going to be equal to whatever this guy holds, right? Lower bound would be equal to the current guy. And so we simply say, well, actually, not really, right? Because we want the lower bound. But what that means is that if we're strictly smaller than something, we're going to go to the last guy of which we were strictly smaller of. I don't know if that was an understandable phrase at all. And so the thing we need to do is simply return the lower bound, right? Yeah, I feel so. So if we need to go to the right all the time, and if we find something that's equal to us, then I think we may have a problem. So else if, right, I think else if the value is different from the current data, this is like greater than, val greater than, or so like val greater than current, and here's val smaller than current, and then equals else. The else case would be whenever val is equal to the current one, in which case we simply return, we just return the current one. And that's all. So this case is really like almost never going to happen. So I'm willing to say, I'm willing to use the Fourier processor and say that this is unlikely. I know it doesn't really help that much, but it is good to have it up there. And then if lower bound never gets set, we do have to set it to a null pointer. All right, I feel like I don't like them in the same line. I just want it to be lower bound is equal to a null pointer. Great. I think this sort of concludes our task with find. Find was relatively simple, which is great. And I think we can simply use that. So this is the test for insertion. 70 lines of code for a single test. How wonderful. Now we're going to test find. So what we are going to do is we're just going to use the same red black tree. I'm actually tempted to just put it on the side to use the exact same thing. We have the red black tree, and then it's an integer, right? And then I have red black tree, and then I just insert all the stuff that we've been inserting so far. So 15, right? Arbitrary 15, arbitrary insert, and then 5. Arbitrary insert, and then 1. Arbitrary insert, and then 12 and 13. 12, insert, and 13. And then arbitrary dot insert 13, 17. 17. And then we insert 19 and then 21. Arbitrary dot insert 19. And then 21. So this is a whole tree, the one we have in the drawing. So right here, this one. 21, and yeah, we continue. So now what we're going to do is we're going to test find. Right? So I'm just gonna say assert that whatever arbitrary.find gives me for the value of 15 is like has as data 15. So like it returns something that has as data 15. And same for some other random value like, I don't know, 17. Right? 17. Or like check exact matches. And we can simply create a vector over here of integers that contains all of the integers that we have in our tree. So 15, 5, 1, 12, 13, 17, 19, 21. And we can simply write a loop that just goes through each of them. And then we should give this a name, so nums. And then we simply assert that whenever the tree finds something related to that number, its data better be equal to that number because it's an exact match. And so now, what we're going to do, non-void function does not return a value. Brother, what are you talking about? Oh, return true. Yeah. True as in we passed. So we are going to assert that, and then check it returns lower bound when not an exact match. So for those of you who tuned into the stream, we are building a red-black tree, and we just a few minutes ago passed the insertion test case, and our insertion for the red-black tree is finished, which is unbelievable. I've been here since 2 p.m. and it's already 10 p.m. I've been streaming for around 7 hours. 7 or 8 hours, yeah. So, well, let's go. You know, programming is a thing, and it's pretty cool, but it demands some time. Now we're gonna check that it returns a lower bound when it is not an exact match. And the way we can do this is we're just simply gonna evaluate cases, right? So whenever we find arbitrary.find, say we request, I don't know, right? 11, right? Then the thing it should return for us should be, sorry, this is not a tree. Our tree has 12 instead of 11. There you go. What it returns for us is 13. Like that's what should happen. Remark on the short and the should, because I don't know if this is on, you know. Oh wait, it's just like okay, exactly. Wait, I thought you were there when we passed uh the insertion thing. It was an epic moment, but it's all right. Yeah, I'm definitely happy. Now I proceeded to start creating finds, but I think find is relatively simple, to be honest. I don't want to say that because then it's like then it starts failing and bad things will happen if it starts failing. It should return 5. So if I try to find 3, brother, why are you failing? Oh, it's just a C++ extension. That's fine. Let's see. If we now trying to find, oh, you were there. Oh, that's great. Yeah. If we're now trying to find, say, 14, we want the best fit to be 15, which is in our tree. What else? If we try to allocate, let's see, if we try to allocate something like 10,000 or 14,000, then this thing should be a null pointer. It should tell us I didn't find anything. Then on the red black tree dot find, whenever we try and find, say, I don't know, 2 or 0, right? 0, then it should return us 1. And let's see, let's create 2 more. If we try to find, say, have we tried to find 14? Yeah. If we try to find 18, then it shouldn't give us 17, it should give us 19. Okay. And the last one. I know. I'm annoying with the test cases, but I hate the test cases are like the thing I hate the most from programming. But I do have to recognize that they're sometimes needed, especially when we're working with such sort of fundamental things like this data structure. So bear with me. I think we have it already. If we try to find 20, oh, dude, no, should be 21. Yeah, you should give me 21. So I think these are all the cases. Let's see. Find 11, you should give me 13. Find 3, you should give me 5, yes. 14, you should give me 15. 14,000, you should give me nothing. 0, you should give me 1. And then 18, you should give me 19. And 20, you should give me 21. Yes, sounds about right. So let's build this. And let's compile it. Perfect! Dude, find first try, we got it. Although the code was very simple. Like I do have to admit. We have marked the case of equality unlikely with the with the I don't know what how do we call this? Do we call this a preprocessor? Because it's not a preprocessor. It's like it's similar to the whole sort of the what's the name? glibc, and then you specify that this is a branch that that is unlikely to be taken, just so that the compiler can take it as a hint for the branch predictor. But I mean, it is sort of kind of clearly known that this often doesn't help. Like it doesn't really make a difference, but it's good to include it either way. Let's see. Perfect. I mean, we have find, and we have insertion. I feel that's already a great thing. Like, awesome. So I think we're going to finally test remove, because as I said, my goal is before it was we will finish insertion. I think that now my goal is we will finish the entire red black tree class. And as I mentioned before, I'm a little bit scared about remove because it is it's a little bit strange sometimes, but that's totally okay. So I think let's take a break. Let's take a break. You and I, the viewer, like the 3 viewers that I have right now. Like, let's take a break, guys, and we'll come back in 10 minutes. So currently it's 10:40. At 10:50. So just add 10 minutes, and we will be back. By the way, in yesterday's stream, I was I was a little bit new. My first day on Twitch. I had never streamed before. As you can see in the title, this is my second day. And yesterday and today's morning, I spent all the time, creating scenes. Did you see that? It's a beautiful transition. Like here I'm coding, and then I'm talking with everyone. And then I have the chat on the side. And then here I have also the chat, but the messages disappear after like 30 seconds. But here it's permanent. Oh, and also have this. Ooh, okay. So I'm just gonna put the little starting soon screen until it's 10:50 for me, 10 minutes from now, and then we will begin again. I'll just stand up to stretch, eat, and like a little snack, and we'll be back. All right. Peace. Right. 10:50 exactly. Here. So yeah, I'm in PST time. So 10:50 already. I hope everyone had a great break. You stood up a little, stretched. Went grab some water just like I did right now. Um, let's see the chat. Pedigree 81 555, and then we just four Illuminatis. Okay, sure. Welcome to the stream. I don't know what else to say. But that's great. That's good. For those of you who are just tuning in, we are working on red black trees because we're gonna use it as the data structure in our memory allocator, and we are now going to proceed to work on the remove. How to remove an element on a red black tree. So this is a very interesting question. And the reason is that usually for red black trees, you can specify the key that you want to remove. The problem is that with our memory allocator, there is really no such thing as a key, right? Whenever somebody calls free, and I think we like, right? Whenever somebody calls free, so over here, if they just say, by the way, the name of our memory allocator is malloc, so malloc. Why? Well, because I don't know. It's like the new malloc or not malloc or just a pirate version of malloc. And if somebody calls malloc, everything is fine. That only involves an insertion. The problem comes if they call free. When they call free, the only thing they pass us is a pointer, right? This pointer, well, we don't. There's sort of no way to have a key for a red black tree that allows it to be efficient while it allows it to be sorted out, right? So the key that we're going to have is, of course, the size of the block. So our red black tree will be ordered with respect to that. The problem is that there could be many blocks of size 50. So if I were to say red black tree, please remove the block of size 50, well, which one, right? We don't want to just randomly free some memory that the user is actually using. We want to free exactly the point, sort of the block of memory that they pass us with that pointer. That means that we need to support random access deletions, right? It means that we're already going to know what is the node that we want to delete, which is a great advantage. What that introduces, though, is the problem that if we're just given a random node, we're not going to know where it is in the tree. If we were to be given the key, we're able to go down the tree to find where that node is, and we would know how to trace our way back. So whenever we need to fix, say, the parent pointer, we would be able to do that. But here we don't. We only have like a random node that they provide, and that's why our memory blocks are required to contain a parent. And this, believe it or not, is a bit of a penalty, right? Because currently in our header, we have, if we were to not have a parent, we would have 1, 2, 3, and 4. So it's sort of 4 fields in our header, each being 4 bytes. Sorry. 4 fields in a header, each being 4 bytes. That'd be 16 bytes. But with this parent, we are making it have 20 bytes. Now you may be saying 20 bytes, that's almost nothing. But when you multiply this or you aggregate this with the amount of blocks that are going to be allocated through the application's lifetime, that is a lot, right? And not only that, but in this small scale, you're going to say, well, 4 bytes is almost nothing. But remember, previously we were using only 16. So 4 bytes is 25% of that. So just for the sake of using a red-black tree, we're incurring an extra 25% penalty. And if we were to have used an AVL tree, we would have incurred in an even bigger penalty, a 50% penalty, basically, because we would not only need the parent to support random access, but would also need the height of the node. That's why we decided red black trees. And that is sort of the context necessary to what remove will look like. Because for remove, we already will know what node we're talking about. And it's also a bit of a problem. A bit of a problem because right now in the red black tree, right, we have remove, sure, but like you need to pass me something, right? You need to tell me what to remove. So we cannot pass the key because the key is going to be like the size, right? It's also not like we're going to have memory blocks have an ID because that means that we're going to have an extra 4 bytes. And if it was for that purpose, we would have just done an AVL tree. So, you know, we have a bit of a conundrum here. What do we pass to remove? Perhaps the answer would be pass me sort of a pointer to the node you want to delete, right? The problem with that is that whenever we insert something, right, we have absolutely no idea of which node is the one that holds the thing we just inserted. So we are confronted with a design choice, which is we could return the pointer to the thing we just inserted, right? But in the case of a memory allocator, that pointer will already be there. So we will already have it available because that's what the user is going to pass to free. So we're going to accept that. And just sort of for the sake of completion, so that this is also a red-black tree that is usable somewhere else, we're going to return from insert the node that we end up inserting. Okay? So node t star, and it is going to be not a reference, not anything. I think this is fine. So we have this constant pointer, and not only is it a constant pointer where we let me think. Yeah, no, that's the const is perfect. But I think we would also need another const, right? So this first const, if I remember correctly, will apply to the data we are pointing at. So this is just saying you cannot modify whatever this is pointing at, because if the user just starts messing with it, then like we're cooked, right? We're done. So you cannot modify the data that's there, but the user could technically still move the pointer and then sort of try and modify whatever's next to it. Well, I think this gets rid of both cases because we just say you cannot dereference it, you cannot do much with it. You can definitely inspect whatever we have. I don't care if you know how my memory layout looks like, because in the end, the one that's going to be using that red-black tree is ourselves in the memory allocator. The memory allocator is the one that has to concern itself with not revealing much of the information. But for now, us, we're just creating the internal data structure, so it shouldn't be a problem. Therefore, we can just return that. And what that implies is that we're going to need to sort of save a reference here called result, right? Which points to the new node. Okay. And then after all of that, because remember that as we go through fixing mistakes, we modified what the new node is just to go up the tree. So it's better if we simply keep track of what the new node originally was and then just return it. So yeah, that's it. We have a return over here. So I'm just going to return the result. Perfect. All right, let's move to remove now. By the way, I know it's really late for some of you. I've been streaming for a long time. Feel free to leave the stream, to enter the stream whenever you want. I'm just gonna be here. Right? I'm here talking to whoever is in the chat, and yeah, that's all. So let's. Okay, now for this, like right now, a feeling of dread invades my being. Why? Because the insertion video, right, from Michael Sample, as you can see, it's 5 minutes and 38 seconds. The deletion video is 8 minutes. Not only that, but it has a second part called Delete Fixes, which is almost 6 minutes long. I don't know about removals in Red Black Tree, so we're going to have to watch both of them. If you already know about red black trees, just take a walk while we learn how to remove stuff from a red black tree.
Better late than never, even if I am 5 years late.
Today we're what? 5 years late? What is he saying? Wait. When was the insertion video?
About red black tree insertions.
Okay, 5 years late. 9 years ago. And when did he post the deletions video?
What if I could build an app that works
my
great.
way? I'm so sorry. I don't have YouTube
My
Premium.
work moves fast.
Better late.
3 years ago. Whoa, that's like a 6-year delay to release the deletions video. That's how scared he was, bro. Like, I'm genuinely terrified of deletions now.
Let's see. Never, even if I am 5 years late. Today we're going to learn about deletion in red black trees. If you're coming across this video before the others, be sure to watch the rest of the playlist first. Let's do a quick review on red black trees.
We already know this.
Break it down to delete the actual node.
Okay.
We'll cover a helper method called transplant. Transplant helps us move subtrees within the tree and is called by our delete method. The delete method handles the logic to delete the actual node.
Okay.
And finally, there's a delete fix-up method.
Oh no.
Which we'll call at the end of delete in order to make sure our tree maintains the properties of a red-black tree and all nodes are properly colored.
Okay.
Let's take a look at transplant. Again, transplant helps us move subtrees within the red-black tree. Here's the code for it.
No! No! Michael, what did you do? No, 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 no. Oh. Yeah, here's the code for it. No! Okay, that's okay. I didn't really look much at the code for transplant. I imagine it's a really simple function. I want to see, does he provide the code for delete? Because delete is what we care about. If he doesn't, then we're clear. Yeah, it seems like he doesn't. Okay, no, yeah, that's fine. So transplant seems like a very simple function, so I think we're good.
Let's take a look at the first condition. Again, this is when U is the root. I'll demonstrate with the tree on the right. For now, I want to completely ignore the color of nodes. Also, I'm intentionally not including any nil nodes, so the slides remain uncluttered. Let's say we want to delete 15. In this case, the calling code, which we'll look at later, would send 15 as U and 19 as V.
Oh.
We set the root equal to V, and we set V's parent equal to U's parent, which is none. So we remove the connection between 19 and 15. Notice there is no code for updating v's left. This is because updating v.left or v.right is the responsibility of the calling function. Let's reset and take a look at the second condition. Again, this is when u is the left child. Let's say we want to delete 12. In this scenario, the calling function would pass 12 as u and 13 as v. U's parent is 15. We set u's parent's left child equal to v. And we set v's parent equal to u's parent, which is 15. Again, updating v's children is the responsibility of the calling function, so we're done.
Okay. Thank you.
Now for the third scenario, where u is a right child.
Okay.
Let's delete 19. The calling function would pass in 19 as u and 23 as v. U's parent is 15. We set 15's right child equal to v.
Okay.
And we set v's parent to u's parent. Again, no updating v's children in this function. That covers transplant. Let's take a look at the delete function and see where transplant is used. I'll group delete into 3 cases. First, when the node we want to delete has a nil left child. Second, when the right child is nil. And lastly, when neither is nil. Let's look at case 1 and delete 19. We'll call this node Z, and I'll explicitly add in the nil node since it's important here. First, we make note of Z's original color, which is black. We label Z's right child X and call transplant, passing in Z and X. The result of the transplant is the following. Lastly, because the original color was black, we need to call delete fixup with node X.
What?
We'll ignore the specifics of the method for now.
Oh, okay.
Just know that it sets node 23 to black.
Ooh, okay, so this seems just like a party of a party of just like mysterious function calls. So delete fixup is just a black box.
On to case 2, where the right child is nil.
Sure.
For this case, I'm going to add a node to the tree, 1, and we'll delete node 5.
Okay.
Again, we'll make note of the original color and label Z's left child as X. We call transplant with Z and X. Here's the result of the transplant function.
And colors are black again. Okay.
Finally, we call delete fixup with X since our original color is black. We're back to a proper red-black tree. Let's look at case 3, when neither child is nil. We'll delete node 12. First, we'll label it Z. I'm going to explicitly add nil for 13's right child, since it will be of importance.
Whoa. Why is so
Later.
far? Oh, I guess it's the in-order successor.
The first step is to find the minimum in Z's right child's subtree.
Yeah, the in-order successor. Okay.
We can see that this is 13, and I'll label that node Y. We'll make note of Y's original color, which is black, and label Y's right child as X. We call transplant, passing in Y and X. The result of transplant is that X moves up into Y's place, and we'll leave Y floating for now. We'll now change some pointers around, setting Y's right child to be node 15, and node 15's parent is now Y.
Okay.
We call transplant once more, passing in Z and Y.
Why?
This time, transplant sets the tree's root to Y. Upon returning to the delete function, we fix our pointers, replacing Z with Y. There's one final step since our original color is black. Notice that this is not a proper red-black tree, as the path down to X doesn't have as many black nodes as the other paths. We call delete fix up with X, and our coloring is fixed.
Oh, so it's not magic. Okay.
In this video, we cover transplant.
Sure. Let's see delete fix up. Maybe that explains a lot of the doubts we have.
Today, I'll conclude the series on red-black trees and explain the delete fix up method that we talked about last time. A quick summary. In the last video, I discussed transplant and the delete function. Today, we'll unpack delete fix up, which fixes any red-black violations.
Okay.
As a reminder, here are the properties of red-black trees. A node is either
We already
red,
know this.
properties are still met. Next, when our original color, but at the very bottom, we
Brother, why will you show me? Okay, Michael, will you show me the code? Let's see. Let's just read. Okay. Oh my God. Oh no. Look at this. What? Okay. Guys, it's 11:11 p.m. where I am. I think we can push. We can continue. Let's see. Deletion in a red-black tree is a bit more complicated than insertion. No, when a node is to be deleted, it can either have no children, one child, or two children. Here are the steps involved in deleting a node in a red-black tree. If the node to be deleted has no children, simply remove it and update the parent node. If the node to be deleted has only one child, replace the node with its child. If the node to be deleted has two children, then replace the node with its in-order successor, which is the leftmost node in the right subtree, because this is in the end a binary search tree, so this makes sense. Then delete the in-order successor node as if it has at most one child. What? What? Okay, I understand. Yeah, 3. After the node is deleted, the red-black properties might be violated. So up until this point, this seems to be usual binary search tree stuff. After the node is deleted, let's see, the red-black properties might be violated. To restore these properties, some color changes and rotations are performed on the nodes in the tree. The changes are similar to those performed during insertion, but with different conditions. Okay. Deletion takes a log in time. That makes sense because you need to check up the tree. Okay. Reference bugs. Okay, sure. Insertion versus deletion. Like insertion, recoloring, and rotations are used to maintain the red-black properties. In the insert operation, we check the color of the uncle to decide the appropriate case. In the delete operation, we check the color of the sibling to decide the Okay, so we need to add someone else to the family. We have the family members. We have grandpa. We have uncle. Now we need sibling. Oh, a new person. Hi, Kalakale. Hello. So I give this introduction to sort of the new viewers. Welcome to the stream. Currently, we're writing a memory allocator from scratch. And you may be saying, well, why are you looking at red-black trees? The reason is we decided to use red-black trees as our data structure for the memory allocator in order to keep track of the free blocks, because it provides very good search time, but it also provides a decent enough memory trade-off compared to other alternatives like AVL trees, right? The problem is that I knew about the existence of red-black trees, but I never really looked into them until yesterday. So I know nothing about them. And I've been streaming since 2 p.m. here where I am. It's already 11:15 p.m. We took a break of 1 hour. So I've been streaming for approximately 9 hours now. We've been working on the red flag tree still, which is very funny. But yeah, I mean, it's all of that. Feel free to get out the stream and enter back again. I don't know. I feel like people are busy. If you're just visiting, that's completely fine. Um, cool. I've written a linear memory allocator, which is simpler. Ooh, okay. Wait, no, that's pretty cool. That's pretty cool. It was one of the choices he had, but I wanted to also get familiar with sort of these other data structures, which is why I decided more on like a best fit policy. And that's exactly why we have been lately descending into hellish corners of programming. Once again, it took us like what 4 hours to get the insertion working on the red black tree. And now, when I open the article, it says deletion in a red black tree is a bit more complicated than insertion. So it's so bad. Currently suffering for my life, but I feel this is a good thing for the mere sake of understanding, which is also the reason why we're writing a memory allocator from scratch. It's just I want to learn, and this is not an assignment for school or anything. It's just self-taught. I'm a college student though, but I want to learn more about this stuff. So where are you from? I'm currently residing in the United States, although I'm not American. But yeah, currently in Pacific time, so I'm in the state of California, and yeah, that's it. And right now, looking at red light trees when it is almost midnight is not sure if a dream or a nightmare. So we will proceed. we'll see. Because it's telling us, let's see, here it says deletion is a fairly, it's morning here. Whoa. Morning? Where are you? Yeah, that's pretty cool, actually. Like the fact that, there's like people all around the world joining the stream. You're in Europe. Oh yeah, that makes sense. I assume the US, so it should be something like, so what? Either 8 a.m. for you or 9 a.m. One of the two. Like 8:17 or 9:17, I imagine. Yeah, 8 a.m. Okay, that makes sense. So you're more like around the parts of France, Spain, Portugal, around that area. That's pretty cool. Pretty cool. But yeah, I mean, we've been, I mean, pretty good you're joining the stream so early. Like I could not imagine waking up and be like, I'm gonna join the memory allocator stream. But yeah, it's really good. Let's see, the main property, the valleys. Also the UK too is also in that timeline. Let's see, the main property that violates after insertions to consecutive rates. So yes, we check for the color of the sibling. That means we need to start going through this. Work starts in an hour, so that's why. Oh, okay, that makes a lot of sense. A lot of sense, yeah. Dude, I don't have work right now, but it's the summer. So I have an internship instead. And I also need to start there at 9 a.m. And it's gonna be, you know, I the goal of today's stream is to finish the red black tree class no matter how long it takes. If I have to stream for 4 more hours, 6 more hours, I'm going to do it. But we are finishing that today. And I have to go to my internship tomorrow at like 9 a.m. That's completely fine. Everything for the sake of programming. I thought you were British because of the accent. Oh yeah, thank you. I'm not from here from from the US. I'm also not from the UK. I've actually never been to England or Scotland, Ireland, either of them. Um, the story of my accent is actually kind of funny. I I I learned English on my own, right? So I sort of learned English self-taught, and I used the computer program to do that. The thing is, the computer program was in the American accent version. So I like the first accent I learned was the American one. The thing is, I learned English when I was very little. I was like 10 years old, 11 years old. So naturally, you ask yourself, like, okay, well, what do I do with this language now? And the best thing that came to mind was like watching Minecraft YouTubers. So as a kid, of course, this is sort of the only thing you can think of, right? Like games or like stuff you're interested in. And I picked YouTubers, and it just so happened that most of the YouTubers I watched were British. So I ended up inheriting their accent. And that's why I have this sort of weird British accent. It sounds weird sometimes because since I've been living here in America, yeah, for some year, um like for college, it has mixed a little bit, so sometimes it like changes and it does like all sorts of weird stuff. But yeah, it's an interesting origin story, I would say. I don't know. And yeah, um I don't know, I wish the accent helped with understanding more, because people say that like British sounds like in the movies, like the scientists and everything are always British. So hopefully that could give us some advantage, but it doesn't seem like it. Um, so yeah, I don't know. Let's see. I mean, we see the main property that violates after insertion is two consecutive breaths. In delete, the main violated property is change of black height in subtrees as deletion of a black node may cause or reduce. No. It violates the third property, which is one of the more difficult ones. Deletion is a fairly complex process. To understand deletion, the notion of double black is used. What are we talking about? Okay. When a black node is deleted and replaced by a black child, the child is marked as double black. The main task now becomes to convert this double black to single black. Okay. Deletion steps, let's see. Following are detailed steps for deletion. So perform standard BST delete. When we perform the standard delete operation in BST, we always end up deleting a node which is an either leaf or has. Oh wait, message in the chat. I see you moved to another country too. Yeah, I'm currently studying in the US. I'm in college in the United States, and yeah, studying computer science and honors mathematics. So this is the reason why yeah, I'm residing in another country for now. I'm on a visa. So yeah, let's perform the standard BST delete. When we perform standard delete operation in BST, we always end up deleting a node which is an either leaf or has only one child. For an internal node, we copy the successor and then recursively call delete for successor. Successor is always a leaf node or a node with one child. So we only need to handle cases where a node is leaf or has one child. Let V be the node to be deleted and U be the child that replaces V. Okay, know that U is null when V is leaf and color of null is considered as black. Okay, if either U or V is red, listen, I was born in Turkey, now working in Germany. Oh, pretty good. Wait, okay, yeah, so that makes a little bit more, like, a little bit of sense with the time zone. Although, I feel like Germany is kind of like in the middle. So I feel like if you go right, then you're going to be like 1 hour behind. Then you go a little bit more left. And I see. Taking working in Germany. I assume you work as like a software engineer, because I mean it takes like a specific kind of person to click on a stream called coding a memory allocator from scratch, right? So most of us are like sort of interested in computer science, mainly low level or stuff like that. Um, I've seen many people dedicated to security uh, are also have joined the stream a lot in the past, um, especially because of the importance of memory and the incredible amount of blocks that occur in exploits that are present precisely due to how memory allocation works and like buffer overflow, stack overflow, like etc. So yeah, that's pretty interesting. Um, I don't know if you're familiar with red black trees. You work in embedded systems, okay? That makes a lot of sense, right? Like it once again takes like a special kind of person to have like a specific interest. And that's pretty cool. Um, I mean, yeah, I wish I could just jump to writing the memory allocator, but before I have to learn whatever this is, um, which doesn't really seem very, uh, very kind to us right now. I don't know. And yeah. Oh, and thank you for following. Yay. Okay. Now we have 6 followers. Let's go. Great. I mean, honestly, my goal with these streams is not to become famous or something like that. It's just to hold myself accountable to finishing stuff, right? And to building stuff with people that are also interested in it and like can provide sort of ideas where we can just talk about all of these things in general. Um, soon, hopefully. I do have to say the Primogen is like one of my like I really like him, right? He's like a pretty cool guy. Really got me motivated. And in fact, this is like the person for which I got the idea of streaming because I was like, dude, I'm struggling with um projects and sort of keeping up with the things I want to do, right? Because it's very hard to find motivation sometimes, especially in an era with AI, with where I feel some of the aspects of discovery and of saying like, this is gonna take me 8 hours. And although I know there are thousands of implementations of red black trees, I just want to learn, right? It's becomes a little bit more difficult. And then I thought about it. I was like, well, why don't we just like create a stream? And then I'm sort of forced to to implement whatever I'm working with. Um, and then I can just get to meet other interesting people in the field. So yeah, and then like hold myself accountable and be like, yes, we have to finish the red black tree today. So yeah, you're feeling the same. I feel losing interest in my profession due to AI. Yeah, I feel I haven't really gotten like a proper job, like a full-time job, but as I said, I'm in an internship. And right now it feels really empty. Like programming, it feels very strange in the sense that, well, two things, right? Like currently in my internship, I'm not really working on anything related to this, to the things I'm interested in, which are like more low level systems programming, C++. Right now, they're making me do like front end and like web stuff that maybe is not that interesting, at least to me. Um, and on top of that, corporations are currently pushing AI a little bit too much. Where they're like, we'll measure your token usage, and the more tokens you use, the better. Although AI speeds some processes up, I feel like it sucks out the soul, like out of programming, at least in a corporate setting, right? Maybe if you're developing a personal project, I think there are ways in which you can find AI and coexist with it and actually make it something useful. But when you have someone behind you trying to tell you like you're on a deadline, right? You need to give us this project now. AI is a new thing, so now I'm gonna give you like 1 day and you better finish it now. It like completely loses all intention. And I have an intern project, as every intern does, but that project doesn't feel mine, right? Like it's completely coded with Cloud Code, and all I do all day is just prompt an AI. So I've decided that these streams are a good way to connect back to like the actual essence of what I found fun in programming. Say, let's see, in work, they shove AI to everything, and that's not why I chose this profession. Exactly. I chose to be software engineer when I was 12 years old looking at forum pages for code blocks. I feel that encompasses everything in the best way possible. There, I don't know, now they're trying to put like AI everywhere, and it's like, use AI, put AI here, take it here, put it there. In where places it doesn't really make much sense, and I'm not sure. I feel like this constant push for AI with unmeasured AI will lead soon to like sort of catastrophic consequences. And I mean, we've seen it, right? Many of the products that are currently being released are not very good, precisely because of the use of AI. And I was working in a bank before my embedded job. Ooh, I see. So do you like more the embedded systems job or the bank? I imagine the embedded systems, given that it's more related to this stream and everything. Although I feel like work at a bank maybe could be interesting too if you were like a software engineer. Because like things about like encryption and distributed databases and distributed systems, it really depends on what a software engineer does. Both are fun in their own. Okay, yeah, that makes total sense. That makes total sense. But I can definitely see why embedded would be better, especially if we are on this stream. So yeah, pretty good, pretty good, dude. Handling real-time money transfers so code had to be performant. Ooh, okay, that is a good. I feel like most of like if you're not doing embedded systems or cybersecurity or something that really needs to speak closely to the hardware, the other way you get to this sort of content is that when you need to have very performant code, um, especially in financial institutions I've seen. When it comes to, well, I'm not sure, like real-time money transfers in between accounts. It's like a pretty difficult problem. There's also all of these things related to like stocks and like stock exchange, etc. that also need very performant code. It's usually like more related to C++ and like very performant code and very memory aware code, and etc., which is pretty interesting. Um, but yeah, dude, this is great. We're uniting all of the the people that are interested in these topics, which is honestly awesome. Um, but yeah, I don't know. Um, right now it's not looking too good because we still have to deal with the deletion of the red black trees. Um, hmm. I'm developing an online game in C++ and stuff like it. Wait, yeah, that's pretty cool. What like as a side project, I imagine that's pretty good. I feel like yeah, I feel like side projects are like the thing that cures sort of burnout. And like when you're sort of tired of the job you're doing and everything, sort of recovering that passion with what you used to enjoy and etc. It's pretty good. Um, I wrote detailed specs for it and decided to use AI to implement a portion of the code. See, there is like I don't feel AI is completely bad to the point where it is intolerable or something similar. I feel yeah, it depends definitely on the use. And if you have control over your project when it comes to writing the game, uh, right, who better than you to decide where AI could be good? I feel that's a pretty good thing. That comes with being the owner of your own project. And yeah, I mean that's amazing. I feel like yeah. It used hash maps where it could use arrays, strings instead of units. In the end, I removed all of it. Never mind what I said, man. Never mind. Well, yeah, use hash maps where you can use arrays, strings instead of even 64. In the end, I removed all of the code and I used AI to just write JSON parts in. Yeah, okay. I mean, I guess it's good either way, right? If it doesn't work, then you still get to enjoy the part of like creating it. Um, I guess it works for the repetitive tasks and stuff like that. AI is also not that good for like when you need performant code. Um, but it is definitely good for those repetitive tasks. Although that was straight, that was crazy. Uh, Comedic timing, where you were like, well, it was using everything the way it should have. Both versions work, by the way. No, I think it makes. I would expect that currently AI tools are getting pretty advanced. So sure, the other version works just below your standards. That also makes sense. Uh, because yeah, I feel like AI could get you there, but if you want something that's more performant, something that looks better, something that feels like your own, also, yeah, definitely there are places where you sort of like there's nothing better than coding it yourself, which in my opinion is great. Um, so yeah, and oh my god, look at this. This is it's gonna be an MOBA game, MOBA game, so unique performance. What is a MOBA game? MOBA game. A MOBA multiplayer online battle arena. Oh, okay. So some genre of strategy video games where two teams of players compete on a enclosed battlefield. So is this similar to like League of Legends? And oh, okay, yeah. League of Legends is like one of the first examples that appears. I see. I've never really played. I haven't really played that many games. You know, all that I've mostly played like what Rocket League, and, and that's kind of it. Um, but this makes a lot of sense. And performance, I imagine, is. See, I feel like games are like one of those unexpected places where the Rocket League is also mobile. Oh, wait, so it just applies to any sort of game where you have teams and then some place where they have to fight in whatever fight means. So I guess like okay, I can see that. Also MOBA. Um, damn. But yeah, I mean, I feel the game is like a perfect place to apply all of this. Because personally, I think it's like one of the things that is the most unexpected to me that games are like the perfect example for something that needs very performant code, something that like better have readable code, something that needs scalability, something that has like a bunch of problems involved with it, distributed systems, how do you coordinate time between the client and the server, etc., etc., etc. So it's very interesting that you're embarking on a game. Um, I don't know. It was definitely one of the things that I didn't expect when coming into sort of low level programming. A lot of the stuff and a lot of the programmers come from the game creation world. Only example that comes to mind is Casey Muratori, of course, legendary programmer. But yeah, there's a lot more people involved in that world, and I feel they're scattered like all around the place. One of my favorite programmers is also this guy called Matt Cladd. He doesn't do games, but he's done a bunch of stuff, especially related to Rust. And he wrote the Rust analyzer, but he also created a financial database called Tiger Beetle, and all of the problems, and remember like all of the problems involved in the creation of that are like awesome and amazing, where you concern yourself with like, all right, we need to make decisions, right? This thing is going to occupy this amount of memory, but we need to consider this trade-off where performance doesn't really correspond to this, and we need more of this stuff, and you pile up all of these decisions that in the end are going to reflect how good criterion, like how good your criterion is when it comes to programming. So it is very interesting, right? In the mere act of writing code, you can also see that reflected. Whether or not your code is readable, I feel it's like a bit of a reflection of how good it was. So yeah, mine, I don't know how readable it is. That'll be for the audience to judge once we're done. And the remove is gonna be a pain. Already calling it. But we will see what happens in the case of removals. Deletions are, yeah, like I like Casey too. Yeah, Casey. I knew Casey because of Primogen, as always. But yeah, I don't know. All of these people sort of inspire you to continue or to keep pushing, right? It is very entertaining. So yeah. Those who have joined the stream, by the way, we are coding a red-black tree. You see that the title says coding a memory allocator from scratch, and you're gonna say, sure, if this is not a memory allocator, this is a red-black tree, and the reason is that we are just using this as a data structure to support lookups for the free blocks in our memory allocator. So since I'm not familiar with red black trees, we're just implementing them from scratch, because when I say that we're writing a memory allocator from scratch, I really mean that we're writing it from scratch. So, all of it just for the sake of learning. And yeah, let's see. We have the cases here where we only need to handle cases where a node is leave or has one child. Let V be the node to be deleted and U to be the child. That replaces V. Da, 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 da. Okay, this case is okay. Sure. Can I see how far you've done in code? Oh yeah, of course. Dude, we have. So all we've coded so far. Yesterday, which was my first day in Twitch, my first stream ever. We were deciding on how things would be organized. So how would memory allocation work? I can guide you through it. We were considering some policies, ended up deciding for best fit. You have two choices here. It's just like, if you want best fit to be performant, you want a binary search tree. You could use AVL trees or red-black trees. The thing is that AVL trees need, apart from left and right, they need to store what the height is of the current node, and that is 4 bytes. Whereas red-black trees need left, right, and they need to store the color, which is 1 bit. So that is like a negligible. And thus, AVL trees, right, compared to red-black trees, represent like a 20% increase in memory usage. When you multiply that across all of the blocks that you're going to have in memory, that really adds up. Because of that, we sort of leaned more toward the red-black tree approach, where we're going to use a red-black tree for lookup when it comes to the free blocks in a memory. And this is what a block in memory will look like. We're going to store the size of the block, the left child, the right child. Both of these are pointers. The parent pointer, and then the color, which is going to be just 1 bit. The size we also store here because of the way sort of memory is laid out. Whenever we need to merge two blocks that are next to each other in free, you mentioned that you wrote a linear memory allocator. So this is probably something you've encountered. And it's the fact that you could enter the scenario of a fake, what's the name? Fake fragmentation. Let's see. Is it C? I thought I saw C++ templates there. Yeah. In the red-black tree, I'm having, so these are two different windows, right? So the red-black tree I'm writing in C++, right? And I'm sort of considering whether or not we want this to be in C or C++. I'm leaning more towards C++, although I think I'll try it out in C. But we're just writing the red-black tree to know how it works, to get familiar with it, to understand it. And once we're done, we can simply, quite literally, just copy the code and put it in our memory allocator. But first, we need to understand how they work, because if not, it's going to come bite us again in the future. That's why you see like the C++ versus the C version. So yeah. So what we have right now is precisely that. This is sort of the memory layout. And yeah, that's sort of like the decisions we've made. The thing is, like I wanted to make it in Z because it's, let's see, well, in C++ you could override new and delete operators of your generic node file. Yeah, exactly. So in C++ it would be easier to sort of put in with the rest of, or it would be easier to implement it, sort of that, or not to implement it, but to put all the pieces together, which is why I was sort of considering doing it in C, because that way we can do it the way it would be done in an operating system, right? Not necessarily sort of like in an operating system, because of course I don't have like an operating system that I can just modify to my will, or at least, well, maybe we do, but that would take a long time. So what I did is I found this lab from Carnegie Mellon University, where they sort of provide these files that allow you to measure sort of the processor cycles, how long they took. You know, you have all these classes that allow you to measure the performance of your code, and then you get just this. Okay, I was explaining something yesterday, some idea I had yesterday, but we just get sort of these functions, and we get sort of a little bit of infrastructure to support us writing the memory allocator. Because if we were to like to connect this to an actual operating system, you would need to do a bunch of paraphernalia that just doesn't really make much sense to do right now, because our interest is the memory allocator. So we just grabbed sort of that infrastructure provided by Carnegie Mellon University, which I'm not enrolled there. I just found it online. so so we're just gonna use that infrastructure. We're gonna implement a memory allocator here. And yeah, so that's most of it. But right now we're focused on the red black trees. And yeah, that's sort of the story. For the red black tree, the code we have right now is this. So we simply have an enum for the color, just because it's better to visualize red and black. And we have our node class, right? Which is, it just stores the information that we need. And then we have the red black tree class, right? So we dedicated most of our time to insertion. All of this time we've been battling with insertion. It took a long time because there were some segmentation faults. There's a reason why this channel is called SharifSegfaults. And oh wait, a new follower, X-Sister. Hi X-Sister, thank you for following. We have 7 followers now. Yay! Okay, yeah. That's the way it is. But yeah, we had insertion. So basically, we handled all of the cases related to insertion, finding the spot where we need to insert, and after that, fixing all of the mistakes or sort of conflicts with the red black tree rules that we may have caused. So case 0, then case 1, case 2, case 3. Return result, right? And then we have find, which allows us to find sort of a block within our red-black tree. And we only have remove left. Other than that, all we have is like helper functions, right? So left rotating a subtree, right rotating a subtree, linking two things together. We have grandpa, we have uncle. Next, we'll have to implement sibling. Then we have the color for data access, shapes, etc., etc., etc. So this is what the code looks like up until this point. I see that my AirPods are running out of battery, and they are the only microphone I have. So let me try and charge them. Let's see if they can survive. So what is the current percentage? Oh, the left one is at 60%. That's awesome. So yeah, now I need to start with remove. So, oh yeah, we also have some tests over here. Testing is, in my opinion, a bit of a boring part of programming, but it is definitely needed, especially when we're coding something so fundamental. So these are the tests for left rotation. Then we have tests for right rotation, and then we have some helper functions, tests for insertion. Whoa! What changed here? Non-void function insert should return a value. Hello, return. Oh, there you go. Anything else? No. Okay, perfect. So we have all of these tests for insertion. We passed all of them like a few hours ago. And now we have the tests for find. Very small tests, by the way, because I'm not going to spend like ages here. And now remove still doesn't have tests because we haven't even implemented it yet. So yeah, it is the difficult life we have to deal with, but it is what we just gotta breathe. We gotta breathe in, breathe out, relax, and then implement remove, I guess, because it's a little bit of a pain, but it is what it is. All right, this we already read. We have the simple case. If either u or v is read. Okay, let v be the node to be deleted, and u be the child that replaces v. Now the u is null when v is a leaf, and color of null is considered as black. U is null when v is a leaf. A leaf. Yes. Okay. That makes sense. So if v is not a leaf, then it's going to be replaced by some child. Sure. If either u or v is red, we mark the replaced child as black. Okay? No change in black height. Note that both u and v cannot be read as v's parent of u, and two consecutive reds are not allowed in red black tree. So if u or v is red, we simply put the guy in, and that's it. So that's not a problem, which is great. We simply delete, and if it's null, we simply okay. So if we don't have children, then deleting the black node is going to be bad. So that's going to be, I guess, another one of the cases. If both u and v are black, then we're going to color u as double black. Now our task reduces to convert this double black to single black. Note that if v is a leaf, then u is null, and color of null is considered black. So deletion of a black leaf also causes a double black. Yeah, okay. So whenever we have the double black, we need to see what happens. When 20 is deleted, it is replaced by null, so the null becomes double black. Now the deletion is not done yet. This double black must become a single black. Okay. Do the following while the current node u is double black, and it is not the root. Okay, for some reason we have a special case if it's the root, apparently. Let sibling of node be s. I assume node refers to u. So if the sibling s is black, and at least one of the siblings, what is this? At least one of the siblings children is red. Perform rotation. Let the red child of S be R. This case can be divided in 4 subcases depending upon positions of S and R. What? Left case. S is the left child of its parent, and R is the left child of S. Or both children of S are red. What? Wait, S is the left child of its parent, and R is the left child of S. Oh, okay, yeah. This is mirror of right case shown in below diagram. The left case, I imagine, is, yeah. S is the left child of its parent, and then R is the right child. Okay. Sure. So we delete 20, we have a double black, and then we enter case 3.2. The sibling is black with at least one red child. Okay. And so sibling S is the right child of its parent and right child of S is red. So this is the right case. And in the right case, we need to... What do we need to do? We need to rotate. But how do we rotate? Oh, I see. We rotate to the left or like to wherever this guy is. We rotate the tree and then we obtain this. Okay. That sounds decent enough. I can live with that. The problem is what happens when you have like the like suppose this guy was black, right? Then when you rotate, you inherit another black. So you cannot really do that. So what would happen in that case? S is the child of its parent. So shown in the below diagram. The right case is S is the right child of its parent and R is the right child of S. Or both children of S are red. Let's see. Right-left case. S is the right child of its parent and R is left child of S. No, but that's easy. Sibling is black with at least one red child. Sibling is a right child of its parent, yes. And the red child R of sibling is the left child of it. Oh, okay, yes, I understand. Then we exchange them. So we perform a right rotation, and after that, we perform a left rotation. This is like a double rotation. Sure. Well, if sibling is black and its both children are black, perform recoloring and recur for parent if parent is black. So let P be a subtree of the complete tree. Yes. Then we delete 10. Case 3.2b is if the sibling is black and its both children are black, then we simply change its color. So perform recoloring and recur for the parent if the parent is black. Why would we need to recur? Recur for 20 to remove double black from it. We delete 10. So that's that. So we recolor and then we transfer the double black to 20. Then we didn't need to recur for parent. We can simply make it black. Yes, I agree. If the sibling is red, left case. Oof, okay. I think. Okay, guys, in all seriousness, this seems to be a little bit more complicated than I expected it to be. It is currently midnight where I am at. And so it's going to I need to wake up early tomorrow. So I think we may make the decision of stopping the stream here. Because the goal for today was actually to implement insertions, and we succeeded at that. And then after that, I said like, nah, let's continue to remove. Like we don't leave until we finish remove. But I feel like I spoke before knowing what I was talking about, and remove seems really bad. I also need to sleep, and the more you stay awake, the less clearly you can think. So I think this may be a good time to sort of finish the stream. Thank you to everyone that joined and to the 3 viewers we have right now. Yesterday, if you were in yesterday's stream, like yesterday I was completely new to Twitch and didn't really know how to set up stuff. But now, as you saw, we we had these scenes, right? Like, I have. Yeah. No, it's very insane. Then again, it needs some time to it. And yeah, that's all. So everyone, have a good day. I feel like most of you are watching from other places. I know that Kele Kele is watching from Germany. So yeah, it makes sense, right? Because currently in Europe the sun is starting to rise, and it's the morning. But hopefully everyone has a good day. I will go to sleep. I'll probably stream tomorrow at what? So I get out of work at like 5 and from my internship at 5. So I'll probably start streaming at around maybe 6:30 from my time. 6:30 PST, which for Europe should be around that's like 3 a.m. I'm so sorry, guys, but yeah, I have to sleep, and like this, the streams don't really coincide with Europe, which is unfortunate. I'll try to do my best though. I'll do my best. I'll start stream at 6:30, and then after that, I'll just continue. I'll keep going until I sort of run out of energy or I need to sleep. And I think I'll try to keep the same habit for every day. And yeah, I don't know. Follow if you like the channel. Um, I'll see you guys like in the future. Um, if I don't ever see you again, well, thank you for coming by, and I hope you join for the future streams. We'll see how how that is possible, because as I said, some of the schedules don't really match with people that are watching from Europe or Asia or other places in the world. So we'll see. But yeah, you know, I hope to see you in the future. I hope to continue doing this, and we will get that memory allocator, and it will be very satisfying, hopefully. So yeah, all right. Bye bye, everyone, and good night, or good morning for some of you. So, yeah, thank you. Bye bye. Tune in for tomorrow's stream, and good luck.